Okay, thank you very much, Mr. Chairman. This is the second lecture. Actually, a continuation of the first lecture. Last time we couldn't conclude, and so this is to be a continuation of our first lecture. So,
Okay.
members can remember that last time we introduced the notion of category, and we have also said that we are going to be following the material and introduction to homological algebras by Joseph J. Rothman. The
Oh,
entire course
awesome.
is Introduction to Homological Algebra, and so we start with the notion of category theory because a better understanding of homological algebra is to use category theory as the framework. Actually, category theory is a tool that is effectively used in homological algebras. So we start with the concept of category theory. And last time we gave an introduction of what category is all about and how it all come to being in 1945 by the work of Samuel Ellenberg and S. McLean. And then we define formally what a category is. If you can remember, we talk about category as being a container consisting of three items. The first item in the container is a class of objects. A class. When we say class here, we mean a collection that is not necessarily a set. You can think of a collection of all sets. We know that from classical set theory, this is not even a set, but it is a proper class. So we have a class whose object are called, whose members are called object, and we have corresponding to any two objects in that class. In the container, there should be a set which we donate by home AB. And home AB is a set of all elements between A to B, which we refer to as morphisms. And then inside the container, there should be also a composition law as to how you can compose morphisms between objects to produce another morphism. We talked about this thing in our last discussion, and then we say these entities are subject to satisfying the following three axioms. And then the first axiom is to say that every morphism, so actually morphisms, you can think of them as mappings between sets. So a morphism is just like a map if you are thinking of the object as set, but this concept is even more general than just taking collection of sets. But if we think of morphisms, if you have F in the home set of A, B, then this should have a unique domain and a unique codomain. In other words, the first requirement is to say that the intersection of any two home sets is empty, that you cannot have a mapping or a morphism or an arrow between two objects with a different source, two different source, and two different targets. This cannot, is not allowed. So every mapping, if you are thinking of mapping, should have a unique domain and a unique codomain. So this is actually the first requirement in the definition of category. And then the second requirement is to say that the composition law that you have in the container should satisfy the associativity property. So the associative law must be satisfied by the composition which you have in the container. That composition should satisfy the associativity. So if you have a morphism from A to B and another morphism from B to C and a morphism H from C to D, then the compositions HGF and HGF, first composing G with F and then composing H with G first. All these three compositions are actually defined, and the requirement is that they must be equal. So HGF must be equal to HGF. So this is associativity law for composition law of two morphisms. And then we also talk about the third requirement, the third axioms is the fact that every object, corresponding to every object, there should be a unique morphism called the identity morphism. So think of it, if the object is a set, then you are saying that there is an identity mapping between any set into it, from the set into itself. So there is a unique morphism 1A, we label it. And the unique morphism should satisfy the property that f times the 1a should be equal to f, and 1b times f should be equal to f. If you think of 1b as a morphism from from b to b, and f is a morphism from a to b. So actually, in the definition of category is what we have given here. Is a container with these three objects or three items inside the container: the class of object, the set of morphisms, the composition law, and subject to three properties, as we explained here. And then we give a lot of examples in order to make this concept clear. And the first of our example is sets. We say sets. And these morphisms, we even say there is a simple notation for how to think about morphisms. When you have f, a morphism from a to b, we think of it as an arrow from a to b, and we write it as a function f from a to b, or mostly written as a to b with an arrow, just like a directed arrow from a to b. So you most of the time think of morphisms as mappings between sets, even though these objects are not necessarily sets. But example, the first natural example of category is the collection of all sets. If you take the set of all sets or collection of all sets, this is a class. In fact, this is not even a set. We saw in the classical set theory, Russell's paradox, when he tried to take the collection of all sets, he discovered that that cannot be a set, and so it is a proper class. So if you take the object, the class of object to be the class of all sets, and so between any two sets, you define morphism, a set of all mappings. So morphism between objects are maps from A to B. So any two objects, you take the collection of all mappings. And so we know we have composition law in this set. We can compose mappings. If you have a map from A to B and from B to C, you can take the composition, which will be a mapping from A to C. And it is also clear that composition of maps is associative, and there is always a mapping from a set into itself, which is the identity mapping, satisfying the given requirement here, actually. So the class of all sets is actually a category, along with the set of all mappings with the composition law. So mappings are thought of as structure preserving maps, actually, between sets. And then if you take the class of all groups, it's also a category, where here the set of all morphisms between object is group homomorphism. And then we have the composition law, and everything is satisfied. And then we talk about AB, the category of all abelian groups. And then morphisms here again are group homomorphisms. And we have the category of all rings. Morphisms are ring homomorphism. In fact, this is giving you, you see, groups, abelian groups, rings, sets, everything is falling as an example. In other words, category is generalizing all this abstract algebraic object. So is some people used to say category is the mathematics of mathematics, or abstraction of the abstract concepts. So you have learned about groups as an abstract algebraic theory, rings but they are now falling as example of another even more abstract concept of category, which we have just described. And so we have commutative rings. If you take the collection of all commutative rings with mappings, preserving mappings, homomorphisms to be the ring homomorphism is again a category. Semi-groups is an example of a category. And then monoids is also an example of category with monoid homomorphism. And then vect F, the set of the collection of all vector spaces, is an example of category with linear transformation as morphisms between vector spaces. If you take all topological spaces, you see even topology is a category. Topological spaces is an example of category where structure preserving maps, morphisms here are continuous mappings between topological spaces. And then we talk about a construction. Actually, from example 1 up to example 9, all this we have given object as sets, because we are saying sets here. And so here groups are sets. Abelian groups are also set. Rings are set. Commutative rings are also set. Actually, this is a typo. It should be commutative cum ring, because we are talking about object in the category of commutative rings. And then semigroups, this semigroup are sets with some operation. Monoid are set, vector spaces are set, topological spaces are sets with a collection of open set, which we call topology. So from the first example up to the ninth example, these are all category whose object are sets. But we talk about category where the object are not necessarily sets. And this is presented in example 10, where we take a partially ordered set and we declare the object, the class of object to be that set, the underlying set of the poset. So we have a set with a partial order structure, and then the element of the partially ordered set are now the object. So you can now see that these are points. You can take the set of natural numbers under the natural partial order. 1 is less than 2, less than or equal to 3, and so on. And so which means here 1, 2, 3, 4, 5 are your objects. So you can see they are not set. And then between any two, think of numbers now, between any 2 points in the partially ordered set, x comma y, you define a home set, the set of morphisms. You describe an arrow from x to y. So there will be an arrow connecting x to y if x is less than or equal to y. And that arrow is labeled kappa xy. So this is just a label to signify that this is an arrow between x and y. And otherwise, there is no arrow between x and y, and so the home set would be empty. So you see, this is a category, and the fact that this is a category is follows from the fact that we have a partial order here. Well, it's a partial order is a transitive binary relation, which is also reflexive and anti-symmetric. And so by the transitivity, we can see that we can compose arrows. If you hand an arrow from x to y and from y to z, you can do the composition of the two arrows to give you an arrow from x to z. So see, an arrow from x to y and from y to z can be composed into an arrow from x to z, precisely because the you are dealing with a partially ordered set here. So the binary operation here is a partial order, is transitive. So we are very sure that we have an arrow from x to z. So therefore, the composition law is well defined here, and the reflexivity of the partial order guarantees the fact that there is always an arrow from x to x. So you can see that uh, we have a category, and this category is called pole of x. So whenever we write like this, we mean x is a partially ordered set, and the object in this category are actually the element in x, while arrows or morphisms are actually existing whenever x is less than or equal to y, and so on. So, and this is a nice construction, and this is general, because once you specialize on this x, you you get so many categories. For example, if you take x to be the set of 0 to n minus 1 natural numbers, 0, 1, 2, 3 up to n minus 1, then you can talk of O of n, and so this is a category where you just have a finite number of arrows. There is an arrow from 0 to 1 because 0 is less than or equal to 1, and from 1 to 2 because 1 is less than or equal to 2. And likewise, there will be an arrow from 0 to 2, and from 0 to 1, and from 0 to 3, and so on. We did not draw. These are the generating arrows, actually. So, and then we also have another special case of this example 10, which we present here in example 12, as to the category of pole of tau, where tau is a topology of some topological space. So if you have a topological space x comma tau, you can view this topology as a partially ordered set under set inclusion. You see, because element of tau are subset of x. So you can say a subset is less than or equal to some other subset if it is contained in it. So you can define a partial order on tau, and then if you replace x in this example 10 by tau, you have a category of pool of tau where object here are open sets in the topological space. This is a nice construction. In fact, this topological space, this category will actually play a role later on uh, in the theory of homological algebra. So we will have occasions where we will encounter this particular category. Okay, and then we also present another example of a topological space of a category where we take the partial order, the reverse partial order on the set of integers. Reverse partial order, we say n is less or equal to n minus 1. This is reverse order. The natural thing is n minus 1 is less or equal to n, but then you reverse the order, and then you now have a category pool of z. And there is another nice construction where you have, when you take any monoid, if you take any monoid, then we can define a category C of M by declaring the class of object to be the set singleton containing the binary operation, because every monoid is a set with an associative binary operation where there is identity. So it is the binary operation now that forms the object in the category. So which means this category has only one object. There's only one object in the category. And then, so which means there will be only one home set, because you have only one object. So you can only talk of the morphism between that object to itself. So we have only one home set, and then the home set will be M. So which means element of the monoid are the morphisms now. So you can now see that this is a category where the morphisms are not even arrows, they are not mappings. In fact, the object is even a binary operation, and morphisms now are element of the monoid. And then you can define a composition law by where if you take a morphism here, which is now an element of the monoid, and you take another element of the monoid, you combine the two, the composition now will be Hg. H star G belonging to M, because you are now composition now is the usual multiplication of M. So you compose, because morphisms now are element of M, you compose them by just doing the ordinary multiplication of M. And so identity will play the role of the identity morphism, because you are in a monoid. In fact, that is why if you replace the assumption that M is a monoid here with a semi-group, you don't get a category. So you can construct a category out of every monoid. So actually this construction is also general, and it is useful in the theory. And then we define the notion in the last lecture, actually, or last discussion, we defined the notion of small, large, and discrete categories. We say a category is small if the object set is a set. We saw so many examples of category where the class of object is not a set. If we go back here, you can see here, the class of object is a set of all sets. This is not a set in the classical, in the sense of Cantorian set theory. This is not a set actually. So you see, this is not a small category, it is a large category. But if you take the class of all groups, is it a set? Maybe it's a set. So if it is a set, then you have a small category. But I can see some category here. For example, this category, you see, this is a partially ordered set. It's already a set. So the class of object is X, is a set. So this is a small category. And again, you have a small category here. And even number 12, because you have a collection, this is a subset of the Cartesian product. And so it is a set. Tau, the topology is always a class of subset. So therefore, the class of object is a set. So this category here is a small category. And this one too is a small category, because the class of object is the set of integers, which is a set. And here you have even just a singleton, which is a set containing only one element. So therefore, this is a small category. So most of the examples we saw are small categories, but we saw an example of a category that is not small. So if the class of object is not a set, then the category is large. It's called a large category. And then we talk about discrete category. That is if the only morphisms are the identity morphisms. So the if you take this, the home set is always empty except when A and B are equal. So if you take any two objects in the category, the home set is always empty except when A and B are equal, where you have the identity. So the only morphisms are the identity morphisms. You don't have any, so which means you only have loops, arrows from this an object to itself. That is called a discrete category, if that happen in a category. So, and then we also talk about the notion of a subcategory. This is always, this is actually the approach in studying any algebraic, any abstract mathematical concept. Once you define a concept, you say sub of that set. You say set, subset, semi-group, sub-semi-group, group, sub-ring, subgroup. You say vector spaces, sub-vectors, subspaces, topological spaces, sub-topological spaces, and so on. So then when we define category, we can think of subcategory. And that means a small part of the category that is also a category in its own right. And that concept should be clear. So once you have a category that is sitting inside another bigger category, in which all the objects in the smaller category are also objects in the bigger category, and all morphisms in the smaller category are morphisms in the bigger category, and that the composition law is the same. So the composition law should be the same. That you compose within the smaller category should be the same composition when you are doing it within the bigger category. So if all these things are satisfied, and even when you are talking about the identity mappings, so if you take an object in this smaller category, the identity morphism from that object to itself should be the same thing as the identity morphism from the object to itself in the bigger category. So if that happened, then S is called the subcategory of C. This is the notion of subcategory. And then a subcategory is said to be full if it contains all morphisms between any two sets of between any two sets. That is it. So what we are saying here is a category is full subcategory. S is a full subcategory if given any two objects in the category S, the set of morphisms between A and B is the same as the set of morphisms. So nothing is left out. You see, actually, there may be proper containment here. Some objects in C may not be object in S. But then any object in S is an object in C. Now, so if all morphisms between any two objects in C are also the same morphisms, if all morphisms between object in C are also morphisms between object in S, then S is said to be a full subcategory. This is the notion of full subcategory. So please, this concept should be clear because we'll just be referring to them in the mentioning them in the throughout the course without any making any reference actually, or having to waste time actually the recalling what they are. So, and in fact, you can look at example of full subcategories here. You see, abelian, the category of all abelian groups is a full subcategory of the category of groups. Because if you take any two abelian groups, they are groups in their own right. Now, if you are looking at them as groups, all group homomorphisms are also the abelian group homomorphisms, because every group homomorphism preserves their identity map. It preserves the commutativity actually. So there is no distinction between homomorphism between two abelian groups and homomorphism between two groups. So if you look at homomorphism between the two abelian groups and look at the homomorphism between those two abelian groups, but treating them as just groups, not necessarily abelian, they are the same set. The set of homomorphism will be the same. So every homomorphism, group homomorphism between two abelian groups in groups will be the same homomorphism between the two abelian groups in the category of abelian groups. And likewise, the category of groups is a full subcategory of monoids, because every two groups are monoid. And if you look at the monoid homomorphism will still be the group homomorphisms. So therefore, these are the same. But monoid is a subcategory of semi-groups. But this is not full, in the sense that you can look at two monoid as semi-group. Now, if you are treating two monoids as semi-group, and you define a semigroup homomorphism, you do not require that the identity must be mapped to themselves. But in defining a monoid homomorphism, you require that the identity must be mapped. So not every semigroup homomorphism is a monoid homomorphism. And so therefore, monoid is not a full subcategory, because there are homomorphisms between two monoids here that are not homomorphisms inside this category here. So this is not a full subcategory. Likewise, when you take groups, it's a subcategory of sets, but it is not full, in the sense that not any two mapping between two groups is a group homomorphism. So if you look at morphisms in set between two groups, they are not necessarily group homomorphisms. And so therefore, they may not be morphisms between two groups which are sets here, are not necessarily group homomorphisms in groups. Because if you want them to be morphisms here, you only need them to be mappings. You do not require them to be structure preserving. But here, the preservation of structure is a requirement. And so therefore, not every maps between any two groups will be seen to be morphisms inside groups. So these are examples that make this concept of subcategory and full subcategory, I believe, very clear. So and another, I think we talk about all these things. I'm just trying to actually revise what we have learned in the last discussion. We also talk about diagram and commutativity of a diagram. In fact, because of our last remark uh, here, where we say if you have a morphism from A to B, we think of it as a map from A to B, or as an arrow. So we normally write an arrow, A to B, meaning there is a morphism from A to B, or F is a morphism from A to B. So in this way, you can develop a graph, because I can have another morphism from B to C. And so then I put an arrow, and I have another morphism from C to some D, or from D to A, to form a cycle, and from A to C again. In that way, you develop a directed graph. So actually, this is what we call a diagram. That graph developed in that way is called a diagram. So a diagram in a category C is a directed multi-graph, because you can have multi arrows, you can have double arrows, you can have so many mappings between a set and another set. From a set A to B, there can be so many mappings. In fact, there will be uh, what is the number of maps? If the cardinalities are finite, you can count the number of mappings that exist from A to B. So you have a multi-graph. So you can have multiple arrows. So it's a directed multigraph whose vertices are objects in object of C, in the set of objects. So, and arrows of that graph are morphisms. So just like what we have demonstrated. And then so we say the diagram is commutative if for any pair of vertices A to B, any two paths from A to B are equal when you compose the path. So I give you examples here. You see, this is a diagram, it's a category, and that's another diagram. And commutativity of the diagram, it means if I'm to travel from A to C, any path I take, it should give rise to the same composition. So in other words, if I say F composed with G, it should give me H. So likewise, K after F should give me what? H. So for this diagram to be commutative, the composition G after F should be equal to K after F, and all that should be equal to H. So it doesn't matter if I compose like this, FG should be FK, and it should also be H. So, and that is what commutativity of a diagram means. So if you are to travel from any vertex to another vertex, whichever route you take, it should give rise to the same composition. And that's the commutativity of a diagram. When you look at this diagram also, if I'm to travel from A to B, I can do it in only one way, from A to B. Now, there F. But from A to D, you can travel FL, or what? KGL. Is that okay? Or KH, and all these compositions should be equal. Or if you are to travel from A to B, we made a mistake there, because from A to B you have two ways. You can travel K, G, and F. So K composed with G should be equal to F. And then likewise from, so you cannot travel from B to C in this graph. And you cannot travel from, you can travel from B to D in only one way, but from C to B is possible in one way, and from C to D also is possible in two ways. So therefore the composition GL should be equal to H. So all these compositions should be equal. So for that diagram to be commutative, that is what we mean by commutativity of the diagram. And this is a language that we adopt throughout our discussion of homological algebras. We will be talking about diagram and commutativity of diagram. So we'll be just saying the following diagram commutes. And once we say a diagram commutes, you should understand this is what we mean. So this is a notion that will be adopted throughout our discussion. And then we also talk about opposite category. The notion of opposite category is actually a dual version of the category, because look at, let me just demonstrate it here. You see, if this is happening in a category, you can decide to reverse all arrows, change the head of all arrows. So reversing. So instead of A to B, you just do B to A. Or instead of what? A to C, you just do C to A. And then likewise, double arrows here from C to B. So you get a new type of, you can reverse arrow to get a new morphism from a target to a source. If you have a morphism from a source to a target, you can reverse the arrow so that you get the reverse. So when you have a category, and inside the category, you reverse all the arrows, you still get a new category. That new category is what is called the opposite of the original category. And that's the notion of opposite category. So given a category, we define its opposite, denoted by COP, to be the category whose objects are the same objects as the original categories. But morphisms here in the opposite are now the reverse. So you can see now, if you have morphism from A to B, now in the new category is from B to A. Every arrowhead is reversed. So this is what is happening. And then composition is achieved in the usual reverse order of the composition. Maybe I just show you. So you have from A to B, and from so you have like this go. So when you reverse the arrows, it will be F opposite and G what? G opposite go. So the composition here is FG or GF normally, right? So if you are reversing, this will be G opposite composed with F opposite, and this should be the opposite of the composition. So this is the opposite of the original composition. So this is actually what we are saying. In order to get the composition, so uh, G opposite composed with F opposite is just the opposite of, you can perform the composition initially inside the uh, original category, and then take the opposite of the composition. This is how you compose in the opposite category. So there is a principle in category theory called principle of duality. And this principle of duality is saying that whatever you can achieve, or any concept you can define in the original category, you can equally define it is dual in the opposite category. So given any property or feature or theorem in terms of diagram or morphisms, we can immediately obtain it is dual by reversing all the arrows. And we are going to be doing this a lot, and adding a prefix co. So we define products and then co-products. So once you define product, to define co-product, you just reverse all the arrows. We define what? Domain and codomain. Domain, codomain. We define kernel, co-kernel. Equalizer, co-equalizer. So this, they will be going hand in hand. So there is this principle of duality. And in order to achieve this result in the opposite, for the dual version, just work in the opposite category. And that is just a very good, clean principle. So we are going to be doing this a lot, actually. We talk about the concept of isomorphism. And we say a morphism in a category. And you should try to understand here, we are trying to generalize concept very well. Don't think of isomorphism. When you hear isomorphism, you think of map. Here, an isomorphism, it can be a point, not necessarily a mapping. We saw category where morphisms are just point numbers. So a number two can be called an isomorphism, or one, maybe it is an isomorphism, something like that in a category existing somewhere. So a morphism is called an isomorphism if there exists another morphism G. So you see reverse morphism. So this is actually like the opposite of the other morphism, called inverse of F, such that G after F is A1 and is 1A, I mean, not the identity morphism on A. And F after G is what? 1B. So you see here, um, we are saying, you see, I used to say G after F. I mean, perform F first, then G. I'm thinking of my composition in the reverse way, actually. I adopt the right hand notation. The argument is written at the right. So when you are composing, G composed with F of X should be G of F of X. So that I will be reading G after F. So F first before G in applying the composition. It's not G first, then followed by F. Okay, and then so we have a theorem here, or a lemma, that the inverse here of an isomorphism is actually unique whenever it exists. So the inverse of F is unique, and so we can denote it by F inverse. We can give it a label bearing F. And this is clear, because if I assume two inverses, then G1 being an inverse, it means G1 1B, because this is the future, this is the property of one, the identity morphism. If you compose with the identity morphism, you get the original morphism. And this is equal to G1. So because G2 is the inverse of F, 1B is FG2. And likewise, you can do the associativity law. You see, this is because you are working in a category, composition law is associative. So I can perform associativity here. And once I do the associativity over here, then I have uh, G1F and then G2. But G1F, G1 being the inverse of F, this is 1A, and then G2. But then the property of 1 is that this composition should be G2. So anytime you have any two inverses, they will turn out to be equal. And so therefore, inverses are unique. And I think this is why we stopped the other time. We were talking about the concept of monic and epic. And this is the concept of monomorphism and epimorphism, or injection and surjection, also called projection. So this is the formal definition of a monomorphism. We say a morphism, which is uh, an arrow from B to C in a category. C is a monomorphism, or called monic. So we'll be using this term monic for short. Monomorphism is also called monic or injection if for all object A in the category and all morphisms F, G from A to B, the composite U after F is equal to U after G will always imply FG. So I think this is better understood in a diagram. So we say U here is a monomorphism if given any two morphisms in the category whose target is B, the source of U, the composite F with U equal to G with U would always imply F and G to be equal. So commutativity of this diagram will always imply F equal to G. So if this happen for all F and G, then we say U is a monomorphism or monic. And this is a general concept of injection, like a kind of, and we can easily prove that in the category of sets, a mapping is a monomorphism or monic or injection if and only if it is one-to-one. So it's one mappings that will satisfy this property. And I think you need to work, please try to prove this, which I have just mentioned, that in the category sets, monic are precisely one mappings. And you will see that if you are working with mapping from A to map, if U is a map and you are having sets here, uh, you will have this to imply F equal to G precisely when U is one-to-one, because it is when U is one-to-one that you can cancel it from the left here. Did you see that? Do you see that this will definitely imply U is 1-1? If this happened, then U must be 1-1. Did you see that? Okay. And uh, if U is also 1-1, this will definitely happen because you have the inverse and everything will work out. So I think this is an easy exercise. You can work it out. And then amorphism in a category is an epimorphism. I think should be an epimorphism or epic or surjection or projection. All these terminologies can be used: projection, epic, monomorphism, surjection. If for all object in the category, with the source of the object is the target of V, you have this composite H after V equal to K after V to imply F equal to G. No, this should be K H equal to, this is a typo, please. This should be K H equal to K. So if whenever this imply H equal to K, then V is an epic or epimorphism or projection or surjection, we call it sometimes. So in fact, you should understand using diagram. You see, if you say V is an epimorphism, if whenever you extend from C to some other object D, the composite V, H after V equal to K after V would always imply H equal to K, then V is an epic or epimorphism. And think about this also in the category of sets and see that it is the onto mappings that will have this property. So this is actually the generalization of the concept of onto maps. And that is why it is surjection. Surjection is a very stronger term than being onto, because suggestion can happen in a more general category. So this is what we are saying. And then this is a concept of initial object. So please, you have to bear with us here because we are trying to introduce this concept so that we can utilize them in our study of homological algebras. That is our target. So this course is not actually a course in category theory, but we need these basics for better understanding of the concept of homological algebras. So sometimes the presentation may be a little bit faster than it should be, but this is because we are heading toward the main aspect of the course. So we define the concept of initial object. We say an object A in a category C is called an initial object if for every object X in C, there is a unique morphism from A to B. So there are always arrows emanating from A. Then there is always a unique from every object in the category. You always have a unique arrow from A to every other object. There is a unique arrow from A to every other object. Then A is an emanating, is an initial object. is the source actually. So, but we would use the term source for the domain of a morphism. So every object in the category is actually a source of some morphism of the morphism. So, but then the initial object, but it will be the source of the associated directed graph. I hope it's okay. So that's the concept of initial object. And so therefore, by the duality, there will be the reverse. The what terminal object, the concept of terminal object is coming immediately. So in sets, the empty set is an initial object because there is always a unique morphism, namely the empty map. Is that okay? From the empty set into every set, you have one and only one mapping, and it is the empty map. The mapping sending nothing to nothing because this is an empty. Okay, so empty set is the initial object, and in the category po of n union 0, 0 is the initial object. There is always an arrow because 0 is less than or equal to every other natural number, and so therefore there is arrow from 0, unique arrow from 0 to every other natural number. So 0 is an initial object. And also in the category of integers, this one doesn't have initial object. It doesn't have initial object. So it is not necessary that there is always initial object in every category. There are categories without initial object, and there are categories with initial object. There are also categories with initial and terminal object, and there are categories with initial, like for example, if we are in this category here, 0 is the initial object because there is arrow from 0 to 1, from 0 to 2, from 0 to 3 all over. And you also see that uh, this is the terminal object because there is always arrow coming to it, unique arrow from every object to every object. So n minus 1 will be the terminal object there. But then there are categories like this category, it doesn't have initial or terminal object. So you can have initial object, you may not necessarily have initial object in a category. But then we have a small lemma that any two initial objects in category, if they exist, they are isomorphic. So you cannot have two non-isomorphic initial objects. They must be the same, up to isomorphism, actually. And this is the proof. If you have A and B are initial object, then there are unique morphisms from A to E. Because by the definition of initial object, there is always a unique morphism from the initial object to every other object. So you have two objects, and both of them are initial object. So which means there is a morphism from A to A prime, because A is an initial object. So there is a unique morphism F. And again, there is a unique morphism F prime from A prime to A. But now if you consider the composite from A to A, because A is also an object, and since A is an initial object, by the definition of A being initial object, there should be an what? A unique morphism from A to A itself. But this composite is from A to A, so it must be identity morphism. So therefore, this composite must be identity. And the other composite must also be identity from A prime to A prime, which means they are inverses of each other, which means F is an isomorphism because it has an inverse, which namely F prime. I hope it's okay. So therefore, you have F to be an isomorphism, which means any two initial objects you assume, they are isomorphic. This is this proof. I don't know why you are sitting so distant away from the screen. Are you seeing it clearly from down there? I'm not sure you are seeing it very well. Okay, so it's okay. So let us continue. All right then. So having talked about the concept of initial object, we now talk about the dual aspect of it, which is a terminal object. So an object in a category B, in a category C, an object B in a category C is called a terminal object if for every object X in the category there is a unique morphism from X to B. So this one is like a sink. The other one is the source actually, and then this is a sink. Everybody is coming into it in a unique way actually. So this is terminal object, and in sets All singleton sets are terminal objects. In what sense? The singletons are terminal objects. So you can have so many terminal objects, you can have so many initial objects, but then we saw in the last lemma that the initial object, whenever they exist, they are isomorphic. Now here we can now see that there are so many initial terminal objects. In fact, all singleton sets are terminal objects because there is always one and only one mapping from any set into a singleton, namely the constant mapping, the constant mapping every element of the set into to one point contained in the singleton. So singleton set are, you have one and only one mapping arrow into it always. So in the category sets, you have the terminal object to be the singleton sets. And then in the category for n, the terminal object n is the terminal object, or n minus 1. Actually, it should be n minus 1 by the way we define it, because the last object is n minus 1. So I think this is a typo. It should be n minus 1. And in the category of the integers, there is no terminal object, because this one is continuing. Actually, you cannot have terminal object there. And we have the dual of that lemma, that any two terminal object in a category, should they exist, are isomorphic. So there is an isomorphism between any two singleton sets. I believe this is clear, because if you have two singleton sets and there's a map from this one, you can just reverse it. And it is always 1, 1. It is reversible. And so therefore, in fact, just apply lemma 17 to the opposite category and you are there. You see, this is the principle of duality that we have talked about. Okay, now the next concept that we are going to talk about is the concept of products. And so by the duality, we will have co-product and so on. So let's C be a category, and then AI be a family of object in the category. So if you take a class of object or a family of object in the category, then a product of that family is a new object in the category denoted by this notation, uh, like A1, A2 up to AN, but the fact is that this index set is not necessarily countable. So you just have a family, and then the product is a new category which we can denote by this, equipped with a family. So actually a product in the category is a pair, or is a product, is an object in the category equipped with another family of morphisms, and these morphisms are expected to be projections. We have defined what a projection is. So equipped with a family of projection from the object which we call the product into each member of the family, such that for every family of morphisms from X, any other category, any other object, into the object in the family, there is a unique morphism from the object X into the product, making this diagram to be commutative. So if you have a family uh, of morphisms, projections Pi from AI into this AI, I mean from the product into AI, and then another family, then for any other family, there should be a unique morphism theta. You know, when we use dotted arrow in a diagram, we mean existence and uniqueness. So there exists a unique morphism theta, so that this diagram is commutative. So any such morphism Fi can be factored in a unique way via Pi. This is what we are saying. Commutativity of this diagram, it means if you compose theta with Pi, it should be equal to Fi. So I think, let me just demonstrate. If the underlying set, the index set here is just a set of 1, 2 elements, which means I have just two members in this family. So the product of two set A1 and A2 is actually a new set which we denote by A1 cross A2, A1 times A2, with projection P1 into A1 and P2 into A2, such that given any two mappings from any other category X into A1, F1, and any two morphism from X into A2, there is always a unique map from X to this product, making this diagram to be commutative. Making this diagram to be commutative, it means theta composed with P1 should be equal to F1, and theta composed with P2 should be equal to F2. So this is the concept of product in a category, product of objects. We will give examples. In sets, product of two objects is their Cartesian product. Okay, product of two objects is their Cartesian product in sets. So we you can I believe you can immediately see that you have projections. If you have two objects, two set A and B, one has these projections A from the set Cartesian product. You can define a map into A by sending a pair A comma B to A and another map, and these mappings will provide you with projections here in the definition. So, and if you have any other mapping, it will be it can be factored in a unique way via this definition. And so I think this map, this definition of this map in theta and the definition of these projections provide us with the verification as to the fact that the product, the Cartesian product, is actually product of two sets in the category sets. And in groups, product of two groups is their direct product. This is generalizing concept. Okay, and then even if in ring, you can talk about direct product of rings and so on and so forth. Okay, I wanted to provide more examples here, but I think uh, these two examples are sufficient here. And then we can, this is a theorem providing us with the uniqueness of products. In other words, if any two products in a category, the products of A1 and A2, should they exist, they are isomorphic. So any two products are isomorphic. Actually, you cannot have two non-isomorphic products, and this is the proof of that uh, uh, theorem. So if I assume C is the product of A and B, and D is also a product of A1 and A2, A1 and A2, you see product is a pair. When you are talking about product of A1 and A2, it's not just the object C. It is the object C alongside, equipped with the what? The projections. So this is a projection and that's another projection. Mapping C into A1 and C into A2. So if this is a product, C is a product of A1 and A2, and D is also a product of A1 and A2, meaning Q1 and Q2 are projections, then we can consider these diagrams. You remember the definition of product. We say if C is the product, then give me any maps, any object, X. Here I'm replacing X with D, and then mappings from D into A1 and D into A2. But I already have maps here from D to A1, the projections. So if I place these projections on top of this C here, then since C is a product, it means there exists a unique morphism theta from D to C, making this diagram commutative. And the same thing I can do for D. There exists a unique morphism psi from C to D, making this diagram to be commutative. And then we claim that this psi is the inverse of this, so that the two are isomorphic. So psi is the inverse of theta, in the sense that one can see it here. For if you consider this composite, if you consider a composite, If you apply psi first and then theta, then the composite is from C to C. Now this composite should be an identity morphism from on C, because if you take this composite here, P1 after theta after psi, what does that mean? It means, look at it, P1 after theta after psi, it means apply psi first, and then P1, oh yeah, and then what? Theta. So if I apply psi first, I get from C to D, and then I apply theta from D to C, and then I apply what? P1 from C to A1. That is the same thing as you can do associativity here. And if you do associativity, if you compose theta, then P1, you get Q1 by commutativity of this diagram. So this P1 after theta should be Q1. But then Q1 after psi is P1, because psi composite Q1 is P1 by the commutativity of this second diagram. So which means this composite is P1. And you can do the same analysis here. You see that P2 after psi after theta after psi is P2. And so what these two equations are saying is that this diagram is commutative. And if this diagram is commutative, it means because C is the product, and by the definition of the product, if you have any mapping from any other category, and you can use X here to be C in the definition, so there should be existence of a unique morphism from C to C by the definition of a product. So which means this should be a unique morphism. But we know in the category we have a morphism uniquely defined from here to here that make this diagram commutative, and that morphism is identity, which means this composite must be the identity morphism by the uniqueness, because we know if we replace this composite here with the identity, it will make this diagram to be commutative. So therefore, by the uniqueness of the morphism existing in the definition of product, this theta after psi must be identity morphism. And then you can do a similar type of analysis to see that psi after theta is also the identity morphism. And so therefore, psi is the inverse of theta. In other words, C and D are isomorphic. And then the dual version is actually to define the notion of coproduct. But before then, we say if the product of any two objects in a category exists, because product may not necessarily exist in a category. But if in a category, give me any two products, the product of the two always exists corresponding to any two objects, then that category is said to have all binary products. So we say it's a category with the property of having all binary products. We'll be using this terminology. I'll just say, let's see, be a category with all binary products, meaning product of any two category in that, of any two object in that category exists. And so, so that is a terminology which we shall be using in the course of the theory. Now, I'm not going to spend much time here because we have talked about principle of duality. So all we did there was to reverse arrows. So in the definition of product, reverse all arrows, you have co-products. The only added requirement here is that the projections, you remember the projections, it was from the product into the AI. It's from the product into the AI. Now, when you reverse arrow, it will be from AI to the product, not product now, co-product. So we donate it by co-product. And then the requirement is that if you reverse arrow, you require that these are alpha I, not pi. Initially, in the definition of product, they were PIs, projections. Now we are using alpha I, they are injections. So you have injections now, and these injections are to satisfy the property here, that when you reverse the arrows, you see that this diagram is commutative. So you see the theta before, it was from X to the product, but now from the co-product, it is injecting down to X. So you have injections, and then this diagram should be commutative, meaning alpha I, then theta should be equal to Fi. And then the same thing here. When you go through it, you see that we are just reversing arrows and then changing the notation from product here to disjoint product. So actually, this is forming a disjointed product. That is what we call co-product. In the category of sets, you form a disjointed product. In the category, you can look at the example here. In the category of sets, if you want to form a co-product of objects, it is formed in this way. You take the Cartesian product of A with the singleton 1 and the Cartesian product of B with the singleton 2, and take that union. That union will be the co-product of two objects or two sets A and B in the category sets. This is the construction. And then also co-product, if they exist in a category, they are unique up to isomorphism. And this proof is the same as the other one, but working in the opposite category by principle of duality. So actually, this is the content of this lecture. In the next lecture, we are going to talk about more concepts in the theory of category. Um, uh, Thank you very much for your attention.
Thank you, Dr. Imam, for the
Mr.
beautiful
Chairman,
lecture.
Mr. Chairman,
Yes, sir. I the